We now want to use the spring potential energy to solve a series of motion problems. Basically, the spring potential energy is just another form of potential energy, like gravitational. The potential energy of a spring is given by U sub s, is the potential energy, and it is equal to 1/2 the force constant k times the square of the displacement from equilibrium. So we have a problem to work through here. A block with a mass of 5 kilograms and a height of 0.5 meters slides down a frictionless ramp, and at the bottom of the ramp it compresses a spring with a force constant of 5,000 newtons per meter. By how much does the spring compress? So at the beginning of the problem, the block has a height of 0.5 meters, and we have the mass, so we know the gravitational potential energy. The block is not moving, so we know that the kinetic energy is 0. The point is, all of the energy is in the form of the gravitational potential energy at the start of the problem. Then the block slides down a frictionless ramp, so no energy is lost to heat because the friction does not do any work on the block. Finally, the block hits the spring and compresses it. So at the moment the spring has fully compressed, all of the energy is now in the form of the potential energy in the spring. If we continue, the spring will push back and move the block to the left, but we want to consider this moment where the spring is fully compressed. The key point here is that all of the energy at the beginning is in gravitational potential energy, and all of the energy at the end is in the spring potential energy. If we know one of these amounts of energy, then we know the other. They must be the same. In our case, we know the gravitational potential energy, we've got the mass, we've got the height, we've got g, so that must be equal to the spring potential energy when it's fully compressed. So to work through this, we first write down our equation for the conservation of energy. The change in kinetic energy plus the change in the gravitational potential energy plus the change in the spring potential energy all must add to 0. The change in the potential energy is the final potential energy minus initial, so this becomes 0 minus mgh since the gravitational potential energy has decreased. The spring potential energy has increased, and that will equal 1/2 kx squared. We can rearrange this to set mgh equals to 1/2 kx squared. Now we can plug in our numbers. The gravitational potential energy here is 25 joules, 5 kilograms times 10 meters per second squared times 0.5 meters. That's then equal to 1/2 kx squared, where k is the force constant of the spring, 5,000 newtons per meter. And if we solve this, we find that x squared is equal to 0.01, and x is equal to 0.1 meters, or 10 centimeters. Okay, let's try a more general form of this question. A block on a frictionless surface here is pushed against a spring that is compressed to distance x. The block is then released and travels up an inclined surface. Find the maximum height of the block. So we've flipped the script here. At the start, all of the potential energy is in the spring, and at the end, all of the potential energy is in gravitational potential energy. We then want to find out how high the block rises using the potential energy. Again, we start by writing down our formula for the conservation of energy. Delta K plus the change in gravitational potential energy plus the change in the spring potential energy has to equal 0. So kinetic energy has to be 0 since the block is not moving, either at the beginning or the end of the problem. The gravitational potential energy is increasing. It starts at the bottom and goes up, so the change is equal to mgh. The spring potential energy is decreasing, so it starts at 1/2 kx squared, and then it goes to 0, so the change is a negative 1/2 kx squared. We rearrange this to set mgh equals to 1/2 kx squared, and this time we solve for h, the height. Plugging this in, we get that height is equal to kx squared divided by 2 times the mass times the gravitational acceleration. That means that the height is proportional to the spring constant and proportional to the square of the spring displacement. This should make sense. The stronger the spring, the higher it goes, and the more you pull it back, then the higher it goes. On the other hand, the height is inversely proportional to the mass, so the heavier the block, the lower the height that it contains, since the changing the mass doesn't change the spring energy. Okay, we have a second question here. So if the spring is compressed twice as much, then by what factor does the height increase? Well, we just found out that the height of the block is proportional to the square of the compression. That means if we compress the spring twice as far, then the height will quadruple. It's 2 squared. All right, on the next question that you guys have to do, I've coded up a similar question to these, except this time it uses 2 springs. That means that you will find the energy stored in the first spring. Then it's going to slide over a surface with some friction. The friction will do some work on the block, slowing it down and transforming some of the energy into heat. Then it will hit a second spring, so you will find the amount of energy in the first spring, the amount of work done by friction, which is the amount of energy transformed to heat, and then whatever energy is left is then put into compressing the spring. All right, good luck.